Gravity holds galaxies together, shapes the motion of planets, and keeps you firmly planted on the ground. Yet compared to other fundamental forces in nature, it is almost absurdly weak. Think about this for a moment. A tiny fridge magnet can easily lift a paperclip, completely overpowering the entire gravitational pull of Earth on that same paperclip. How is this possible? The force that we experience every single day, the one that governs the motion of planets and stars, is actually the weakest of all fundamental forces in the universe. This seems like a contradiction, doesn't it? How can something so important be so incredibly feeble at the same time? This puzzle has captivated physicists for decades, and the answer takes us on a journey to the very edges of modern physics, where we encounter mind-bending concepts like extra dimensions, quantum field theory, and the deepest mysteries of space-time itself. By the end of this exploration, you will understand why gravity's apparent weakness might actually be the key to our very existence, and why this gentle giant of the cosmos operates so differently from every other force we know. The story of gravity's weakness is really the story of why our universe works the way it does, and it reveals some of the most profound secrets about the nature of reality. Every time you drop something and watch it fall, you are witnessing one of the universe's greatest mysteries in action. The force pulling that object downward is the same force that keeps massive stars from flying apart. Yet, it is so weak that electromagnetic forces in your body can easily resist it. You can jump, you can lift objects, you can even use a simple balloon to defy gravity temporarily. No other fundamental force behaves this way. The electromagnetic force that powers your phone is trillions of times stronger. The strong nuclear force that holds atomic nuclei together is even more powerful. So why does gravity seem to get such special treatment? Why does it get to be the universal architect while remaining so surprisingly gentle? The answers lie in some of the most cutting-edge theories in physics, from string theory to quantum mechanics, and they might just change how you see the cosmos forever. This is not just a story about physics. It is a story about why we can exist at all in this strange and wonderful universe. When scientists first began to understand the true weakness of gravity, they were shocked. Here was a force so feeble that it takes the entire mass of Earth to keep you from floating away, while a simple piece of amber rubbed with fur can attract small pieces of paper with electromagnetic force. The numbers are staggering. If you could somehow turn off all the other forces in the universe and leave only gravity, the world would look completely different. Atoms would not exist because electromagnetic forces hold electrons to nuclei. Matter as we know it would collapse because the strong nuclear force keeps protons and neutrons bound together in atomic nuclei. Yet gravity, this seemingly insignificant force, is the only one that managed to build the cosmic architecture we see around us. Stars, planets, galaxies, and the entire large-scale structure of the universe all owe their existence to gravity's patient, persistent pull. It is a force that never gives up, never cancels out, and always adds up over time. While other forces can push and pull in different directions, gravity only knows how to attract. Every particle of matter in the universe is constantly pulling on every other particle, creating an invisible web of attraction that spans billions of light years. This cosmic web is so vast and complex that we are only now beginning to understand its true nature through advanced computer simulations and space telescopes. The weakness of gravity is not a bug in the universe's design. It might just be the most important feature that makes everything else possible. Consider this remarkable fact. If gravity were just slightly stronger, stars would burn through their fuel so quickly that they would die long before planets could form and life could evolve. If it were much weaker, matter would never clump together enough to form stars in the first place. The universe would remain a cold, dark, empty void forever. gravity's weakness appears to be perfectly tuned for a universe that can support complexity, structure, and ultimately life itself. This raises profound questions about why the universe has the properties it does. Are we living in one of countless universes where only a few happen to have the right conditions for existence? Or is there some deeper principle that requires gravity to be exactly as weak as it is? These questions push us to the frontiers of theoretical physics and cosmology. Scientists have proposed everything from extra dimensions that dilute gravity's strength to fundamental symmetries that determine the relative strengths of all forces. Some theories suggest that what we perceive as gravity's weakness is actually an illusion caused by our limited perspective on higher dimensional reality. Others propose that gravity itself might be a composite force, made up of more fundamental interactions that we have not yet discovered. The search for answers has led to some of the most ambitious experiments in human history. From particle accelerators that probe the smallest scales of reality to gravitational wave detectors that can sense ripples in space-time itself. Each new discovery brings us closer to understanding why gravity is the way it is and what that means for our place in the cosmos. The mystery of gravity's weakness is far from solved, but the journey to understand it has already revolutionized our understanding of physics and our universe. To understand why gravity is so remarkably weak, we first need to meet all four fundamental forces that govern everything in our universe. These forces are the building blocks of reality itself, the invisible architects that shape every atom, every star, and every galaxy we see around us. Each force has its own personality, its own domain of influence, and its own unique way of interacting with matter. Think of them as the four fundamental characters in the greatest story ever told. The story of how our universe works at its most basic level. The first and most familiar to us is gravity itself, the force we experience every moment of our lives. Gravity is unique among all forces because it only knows how to attract. While other forces can push objects apart or pull them together depending on the circumstances, gravity is always pulling, always trying to bring matter closer together. It acts on anything that has mass or energy, which means it acts on absolutely everything in the universe. There is no such thing as negative mass that could repel gravitational attraction, no anti-gravity particles that could cancel out gravity's pull. This makes gravity fundamentally different from all other forces. Gravity also has infinite range, meaning that every particle in the universe is gravitationally attracted to every other particle, no matter how far apart they are. The attraction gets weaker with distance, following the famous inverse square law that Newton discovered centuries ago, but it never completely disappears. Right now, you are being pulled by the gravitational attraction of distant galaxies billions of light years away. The pull is incredibly tiny, far too small to notice, but it is there nonetheless. This infinite reach is what allows gravity to shape the large-scale structure of the universe, creating the cosmic web of galaxy clusters and superclusters that astronomers observe today. Gravity is proportional to mass, which means that more massive objects create stronger gravitational fields. Double the mass of an object, and you double its gravitational pull. This simple relationship has profound consequences for how the universe evolved from the smooth, nearly uniform conditions after the Big Bang to the rich tapestry of structures we see today. The second fundamental force is electromagnetism, and it is vastly more powerful than gravity in almost every context you can imagine. Electromagnetism acts on particles that carry electric charge, and unlike gravity, it can both attract and repel. Particles with opposite charges attract each other, while particles with the same charge push each other away. This push and pull dynamic creates incredibly complex and varied behavior that gravity, with its simple attraction-only rule, cannot match. The electromagnetic force is responsible for holding atoms together by attracting negatively charged electrons to positively charged nuclei. It creates the chemical bonds that hold molecules together and gives matter most of its everyday properties. When you touch something and feel its texture, when you see light reflecting off surfaces, when you experience heat or cold, you are experiencing electromagnetic phenomena. The force that keeps your feet from sinking through the floor is not gravity pulling you down, but electromagnetic repulsion pushing back up as electrons in your shoes repel electrons in the ground. Electromagnetism also has infinite range like gravity, but because positive and negative charges tend to cancel each other out in bulk matter, we do not usually experience long-range electromagnetic effects in our daily lives. However, when charges are separated or moving, electromagnetic effects can be dramatic and far-reaching. Lightning is a spectacular example of electromagnetic forces in action, as is the aurora that dances in Earth's polar skies when charged particles from the sun interact with our planet's magnetic field. The strength of electromagnetic forces compared to gravity is almost unimaginable. If you could somehow turn off electromagnetic forces and leave only gravity to hold atoms together, every atom in your body would instantly expand to roughly the size of the entire solar system. The electromagnetic attraction between an electron and a proton in a hydrogen atom is about 10 to the 36th power times stronger than their gravitational attraction. This means electromagnetic forces dominate completely at atomic and molecular scales. The third fundamental force is called the strong nuclear force, and it is by far the most powerful force in nature. The strong force is responsible for binding quarks together inside protons and neutrons, and for holding protons and neutrons together inside atomic nuclei. Without the strong force, there would be no elements heavier than hydrogen, no chemistry as we know it, and no possibility for the complex structures that make life possible. The strong force gets its name from its incredible strength. It is roughly 100 times more powerful than electromagnetic forces and about 10 to the 38th power times more powerful than gravity. However, the strong force has a very limited range. It only operates over distances comparable to the size of atomic nuclei, about 10 to the minus 15 meters. This extremely short range means that the strong force, despite its incredible power, has no influence on anything larger than individual atoms. The strong force also has some very unusual properties that make it quite different from gravity and electromagnetism. While gravity and electromagnetic forces get weaker as particles move farther apart, the strong force actually gets stronger as quarks try to separate from each other. This property, called confinement, means that you cannot pull individual quarks out of protons and neutrons no matter how much energy you apply. The harder you try to separate quarks, the stronger the force that holds them together becomes. This is why we never see isolated quarks in nature. They are always found bound together in groups called hadrons. The strong force is mediated by particles called gluons, which carry the force between quarks in much the same way that photons carry electromagnetic forces between charged particles. But unlike photons, which are electrically neutral, gluons themselves carry the strong force charge, which creates complex interactions that are still not fully understood despite decades of intensive research. The fourth and final fundamental force is the weak nuclear force, which is responsible for certain types of radioactive decay and plays a crucial role in the nuclear reactions that power the sun and other stars. The weak force is much weaker than both electromagnetic and strong forces, but it is still enormously stronger than gravity. In fact, at the energy scales where the weak force operates, it is about 10 to the 25th power times stronger than gravity. The weak force has an extremely short range, even shorter than the strong force, operating only over distances of about 10 to the minus 18 meters. This makes it irrelevant for most everyday phenomena, but absolutely essential for certain nuclear processes. The weak force is responsible for beta decay, the process by which neutrons inside atomic nuclei spontaneously transform into protons, electrons, and neutrinos. This process is what makes certain isotopes radioactive and allows nuclear reactors and nuclear weapons to function. The weak force also plays a vital role in the nuclear fusion reactions that power stars. In the core of the Sun, the weak force allows protons to combine and form heavier elements, releasing the energy that eventually reaches Earth as sunlight. Without the weak force, stars could not shine, and the universe would be a cold, dark place. The weak force is mediated by particles called W and Z bosons, which are much more massive than the photons that carry electromagnetic forces, or the massless gluons that carry the strong force. This large mass is part of what gives the weak force its extremely short range and helps explain why it appears weak compared to electromagnetic forces at low energies. When we look at all four fundamental forces together, a striking pattern emerges. At the scales of individual particles and atoms, gravity is completely negligible compared to the other three forces. Electromagnetic, strong, and weak forces dominate the behavior of matter at small scales, determining the properties of atoms, molecules, and the nuclear reactions that power stars. Gravity only becomes important when we consider very large masses or very large distances, scales where the other forces either cancel out or become irrelevant due to their limited range. This is why physicists often say that gravity is the weakest fundamental force, even though it is the force that dominates the largest structures in the universe. The hierarchy of force strengths is one of the most important and mysterious aspects of our universe. Why should gravity be so much weaker than the other forces? Why should the forces have the particular strengths they do? These questions go to the heart of some of the deepest problems in theoretical physics and may hold keys to understanding the ultimate nature of reality itself. The standard model of particle physics, our most successful theory of fundamental forces and particles, can describe electromagnetic, strong, and weak forces with incredible precision, but it treats gravity as a separate phenomenon that must be described by Einstein's theory of general relativity. This separation suggests that our understanding of the fundamental forces is still incomplete, and that there may be deeper connections between them that we have not yet discovered. The quest to understand why these forces have the strengths they do has led physicists to propose grand unified theories that attempt to show how all the non-gravitational forces are actually different aspects of a single, more fundamental force. These theories suggest that at extremely high energies, much higher than anything we can currently achieve in particle accelerators, the electromagnetic, strong, and weak forces merge into a unified electroweak force. And at even higher energies, this unified force merges with the strong force into a grand unified force. Some theories go even further, proposing that at the highest possible energies, near the Planck scale where quantum effects of gravity become important, all four fundamental forces, including gravity, merge into a single theory of everything. These ideas remain highly speculative, but they point toward a deeper unity underlying the apparent diversity of fundamental forces. The relative strengths of the four forces also determine many of the basic properties of our universe. If the strong force were slightly weaker, atomic nuclei would not be stable and only hydrogen would exist. If it were slightly stronger, protons and neutrons would bind together so tightly that hydrogen itself would not be stable, and there would be no nuclear fuel for stars to burn. If the electromagnetic force were much stronger or weaker, atoms would not be able to form stable electron shells, and chemistry as we know it would be impossible. If the weak force were much different in strength, the nuclear reactions in stars would proceed at very different rates, dramatically altering stellar evolution and the production of heavy elements that are essential for planets and life. The fact that all four forces have strengths that allow for a rich, complex universe full of diverse structures and phenomena suggests either remarkable cosmic coincidence or some deeper organizing principle that we do not yet understand. Perhaps most mysteriously, gravity stands apart from the other three forces, not just in its weakness, but in its fundamental nature. While electromagnetic, strong, and weak forces are all described by quantum field theories that treat forces as arising from the exchange of virtual particles, gravity in Einstein's general relativity is described as the curvature of space-time itself. Mass and energy tell space-time how to curve, and curved space-time tells matter how to move. This geometric view of gravity is completely different from the particle-based view of other forces, and attempts to reconcile these two descriptions have led to some of the most challenging problems in theoretical physics. String theory, loop quantum gravity, and other approaches to quantum gravity all attempt to describe gravity in the same quantum mechanical framework as the other forces, but so far, none have achieved complete success. The weakness of gravity makes these theories extremely difficult to test experimentally, since quantum gravitational effects only become important at energies and length scales far beyond what current technology can probe. This experimental challenge means that our understanding of gravity's fundamental nature remains incomplete, and the mystery of why it is so much weaker than other forces remains unsolved. The study of fundamental forces has revealed that our universe operates according to principles that are far stranger and more wonderful than our everyday experience might suggest. And the puzzle of gravity's weakness may be the key to unlocking even deeper mysteries about the nature of reality itself. To truly appreciate just how weak gravity is compared to other fundamental forces, we need to dive into the numbers that reveal the staggering difference in strength between gravity and its cosmic siblings. These numbers are so extreme that they challenge our ability to comprehend them, yet they are fundamental to understanding why our universe works the way it does. At the heart of gravity's weakness lies a tiny number called Newton's gravitational constant, represented by the letter G. This constant determines the strength of gravitational attraction between any two masses in the universe, and its value is 6.674 times 10 to the minus 11 cubic meters per kilogram per second squared. This number might not seem particularly meaningful at first glance, but it represents one of the most important and mysterious constants in all of physics. The fact that G is so incredibly small compared to the constants that govern other fundamental forces is what makes gravity so weak. To put this in perspective, imagine trying to feel the gravitational attraction between two 1 kilogram masses placed 1 meter apart. The force between them would be only 6.67 times 10 to the minus 11 newtons, which is roughly equivalent to the weight of a single bacterium. You could never feel such a tiny force, even with the most sensitive instruments available to early scientists. This is why gravity was the last of the fundamental forces to be understood mathematically, and why Einstein's general relativity was such a revolutionary breakthrough when it provided a deeper understanding of gravity's true nature. The weakness of gravity becomes even more apparent when we compare it directly to electromagnetic forces. Consider two protons sitting next to each other in an atomic nucleus. These protons carry positive electric charge, so they repel each other electromagnetically with tremendous force. At the same time, they attract each other gravitationally because they both have mass. The electromagnetic repulsion between these two protons is approximately 10 to the 36th power times stronger than their gravitational attraction. This means that if electromagnetic force is like a powerful hurricane, gravitational force is like a gentle breeze that you can barely detect. To visualize this enormous difference, imagine that the electromagnetic force between two protons is represented by the weight of a fully loaded freight train. The gravitational force between the same two protons would then be represented by the weight of a single grain of sand. Even this analogy fails to capture the true magnitude of the difference, because the ratio between a freight train and a grain of sand is only about 10 to the 9th power, while the ratio between electromagnetic and gravitational forces is 10 to the 36th power. We simply do not have everyday objects that differ by such enormous factors to make a truly accurate comparison. This vast difference in strength has profound implications for how matter behaves at different scales. At the scale of atoms and molecules, gravity is completely irrelevant. The electromagnetic forces that hold electrons in their orbits around atomic nuclei are so much stronger than gravity that we can completely ignore gravitational effects when studying atomic physics or chemistry. When you learn about how atoms bond together to form molecules, or how electrons move through materials to create electric currents, gravity plays no role whatsoever. The strong nuclear force that holds protons and neutrons together in atomic nuclei is even more dominant, overpowering gravity by an even larger factor. In the world of the very small, gravity might as well not exist at all. This is why particle accelerators, which study the behavior of fundamental particles at extremely high energies, rarely need to consider gravitational effects. Even when particles are accelerated to nearly the speed of light and achieve enormous energies, the gravitational forces between them remain negligible compared to electromagnetic and nuclear forces. Yet despite its weakness at small scales, gravity has one crucial advantage that allows it to dominate at large scales. Unlike electromagnetic forces, which can be attractive or repulsive depending on whether charges are opposite or like, gravity is always attractive. There is no such thing as negative mass that could repel other masses gravitationally. This means that as you add more and more matter together, gravitational effects always add up in the same direction. Electromagnetic forces, on the other hand, tend to cancel out in large objects because matter usually contains equal amounts of positive and negative charge. The strong and weak nuclear forces have such short ranges that they become irrelevant once you move beyond the scale of individual atomic nuclei. Gravity's combination of infinite range and purely attractive nature allows it to gradually accumulate strength as more and more matter comes together, until it eventually becomes the dominant force at astronomical scales. The everyday examples of gravity's weakness are all around us, yet we rarely stop to think about their implications. When you use a simple refrigerator magnet to pick up a paperclip, you are witnessing electromagnetic forces easily overpowering the gravitational pull of the entire Earth on that paperclip. The Earth's mass is approximately 6 times 10 to the 24th power kilograms, and it is pulling on that paperclip with the combined gravitational attraction of every atom in the planet. Yet a tiny magnet weighing just a few grams can completely overcome this enormous gravitational force with its electromagnetic field. This demonstrates not just gravity's weakness, but also the incredible strength of electromagnetic forces when they are not cancelled out by opposite charges. The magnet can lift the paperclip because its magnetic field aligns the magnetic domains in the iron paperclip, creating electromagnetic forces that are vastly stronger than gravity. Similarly, when you jump off the ground, you are using the electromagnetic forces in your muscles to temporarily overcome the gravitational attraction of an entire planet. Your muscles work by using electromagnetic forces to move charged ions across cell membranes, which triggers electromagnetic interactions between protein molecules that cause muscle fibers to contract. These electromagnetic forces, powered ultimately by the chemical energy stored in your body, are strong enough to accelerate your entire body upward against Earth's gravitational pull. From gravity's perspective, this is a remarkable feat. A tiny biological system, using nothing but electromagnetic and chemical forces, can temporarily defeat the combined gravitational attraction of a planet containing over 10 to the 50 atoms. This would be impossible if gravity were as strong as the other fundamental forces. The weakness of gravity also explains why we can have stable planetary orbits, and why the universe has not collapsed under its own gravitational attraction. If gravity were as strong as electromagnetic forces, planets would spiral into their stars almost immediately, and the entire universe would collapse into black holes within a tiny fraction of a second after the Big Bang. The delicate balance between gravity's attractive pull and the orbital motion of planets depends critically on gravity being just weak enough to allow stable orbits over billions of years. This same weakness allows galaxies to maintain their spiral structure for billions of years, giving time for stars to form, evolve, and create the heavy elements necessary for planets and life. When we measure gravitational effects in laboratory experiments, the weakness of gravity presents enormous technical challenges. The first direct measurement of Newton's gravitational constant was not achieved until 1798, more than a century after Newton formulated his law of universal gravitation. Henry Cavendish accomplished this feat using an incredibly sensitive apparatus called a torsion balance, which could detect the tiny gravitational attraction between lead spheres weighing just a few kilograms. Even with this sensitive equipment, Cavendish had to take extraordinary precautions to eliminate vibrations, air currents, and electromagnetic effects that could overwhelm the tiny gravitational signals he was trying to measure. Modern measurements of the gravitational constant still require similar precautions and represent some of the most challenging precision experiments in physics. The weakness of gravity also makes it the least precisely known of all fundamental constants. While we can measure the charge of an electron or the speed of light to incredible precision, measurements of Newton's gravitational constant still have relatively large uncertainties. This is because gravitational forces are so weak that they are easily overwhelmed by other effects, making it difficult to isolate pure gravitational interactions in laboratory experiments. Even today, different experimental methods for measuring G sometimes give results that disagree slightly, highlighting the ongoing challenges in studying the weakest of all fundamental forces. Despite centuries of study, gravity remains in many ways the most mysterious fundamental force, partly because its weakness makes it so difficult to study in controlled laboratory conditions. The implications of gravity's weakness extend far beyond laboratory experiments and into the deepest questions about the nature of reality itself. The fact that gravity is so much weaker than other forces suggests that our current understanding of fundamental physics is incomplete. There may be hidden dimensions, new particles, or exotic forms of matter that we have not yet discovered, all of which could help explain why gravity appears so weak from our limited perspective. The search for these missing pieces of the cosmic puzzle drives some of the most ambitious experiments and theoretical investigations in modern physics, from the hunt for extra dimensions to the quest for a theory of quantum gravity that can finally unite all the fundamental forces into a single, coherent framework. To really grasp the absurdity of gravity's weakness, consider this thought experiment. Imagine you could somehow increase the strength of gravity to match that of electromagnetic forces. What would happen to our world? First, every atom in your body would collapse instantly. The gravitational attraction between the protons and electrons in each atom would become so strong that atoms could not maintain their normal structure. The delicate balance of forces that allows electrons to orbit atomic nuclei would be completely destroyed. Matter as we know, it would cease to exist in any recognizable form. Even before that happened, the Earth itself would undergo catastrophic changes. The gravitational attraction between every particle of matter in the planet would become so intense that the Earth would collapse into an object smaller than a pinhead in a fraction of a second. The Sun would suffer an even more dramatic fate, collapsing into a black hole almost instantaneously. In fact, if gravity were as strong as electromagnetic forces, no stable structures larger than elementary particles could exist anywhere in the universe. This thought experiment reveals something profound about the relationship between gravity's weakness and the existence of complexity in our universe. The fact that gravity is so much weaker than other forces is not a design flaw or cosmic accident. It is actually essential for the existence of atoms, molecules, planets, stars, galaxies, and ultimately life itself. If gravity were any stronger, the universe would be a very different and much simpler place. It might consist of nothing but elementary particles and black holes, with no possibility for the rich structures and phenomena that make our universe so interesting and habitable. This realization has led some physicists to propose that gravity's weakness is an example of the anthropic principle, the idea that the fundamental constants of nature must be compatible with the existence of observers like ourselves, simply because we are here to observe them. The measurement challenges posed by gravity's weakness have driven remarkable innovations in experimental physics. Modern experiments designed to test Einstein's theory of general relativity or search for deviations from Newton's law of gravitation require some of the most sensitive instruments ever created. Gravitational wave detectors, like LIGO, can measure distortions in space-time that are smaller than 1/10,000th the width of a proton. These experiments must be isolated from every conceivable source of vibration and electromagnetic interference, often requiring underground facilities, elaborate suspension systems, and ultra-high vacuum chambers. The weakness of gravitational effects means that even tiny environmental disturbances can overwhelm the signals that physicists are trying to detect. Laboratory tests of gravity at short distances face similar challenges. Experiments designed to look for deviations from Newton's inverse square law at millimeter scales must account for electromagnetic forces, surface effects, temperature variations, and countless other sources of systematic error. The gravitational forces being measured are so weak that they can be affected by the gravitational pull of nearby mountains, the changing position of the moon, or even the motion of cars on distant highways. These experiments have pushed the boundaries of precision measurement and have led to new techniques that have applications far beyond gravitational physics. The weakness of gravity also creates unique opportunities for testing fundamental physics. Because gravitational effects are so small, any deviation from the predictions of general relativity or Newton's law of gravitation could indicate the presence of new physics. Extra dimensions, new fundamental particles, or modifications to gravity at short distances might all produce detectable effects in sufficiently sensitive experiments. The search for these subtle deviations has become a major focus of experimental gravity research, with the potential to revolutionize our understanding of fundamental physics. Perhaps most remarkably, the weakness of gravity allows us to study the universe on scales and with precision that would be impossible for stronger forces. Astronomers can track the orbital motion of planets, stars, and galaxies over long periods of time, building up detailed maps of how gravitational forces shape cosmic structure. The predictable, weak nature of gravitational interactions allows us to calculate the orbits of spacecraft with incredible precision, enabling missions to distant planets and the placement of telescopes at special points in space where gravitational forces balance. If gravity were much stronger, the solar system would be a chaotic, unpredictable place where long-term orbital calculations would be impossible and space exploration would be far more difficult. The question of why gravity fails to dominate at small scales reveals one of the most fascinating aspects of how our universe is organized. While gravity shapes the largest structures in the cosmos, from solar systems to galaxy clusters spanning millions of light years, it becomes virtually irrelevant when we zoom down to the world of atoms, molecules, and everyday objects. This dramatic shift in importance as we change scales is not just a curious detail about physics. It is fundamental to understanding why matter can exist in the rich variety of forms we see around us. The answer lies in the unique properties of each fundamental force and how they behave differently as we move from the microscopic to the macroscopic world. At the smallest scales, where individual atoms and molecules interact, electromagnetic forces completely dominate the behavior of matter. These forces are responsible for virtually everything we experience in our daily lives, from the colors we see to the textures we feel, from the chemical reactions that power our bodies to the structural integrity of every material object around us. When we examine what holds atoms together, we find that gravity plays absolutely no role whatsoever. The electrons that orbit atomic nuclei are held in place entirely by electromagnetic attraction to the positively charged protons in the nucleus. The electromagnetic force between an electron and a proton in a hydrogen atom is approximately 2 × 10⁻³ times stronger than the gravitational force between them. This means that if we tried to hold an electron in orbit around a proton using only gravity, the orbit would have to be roughly the size of the observable universe for the gravitational force to be strong enough. Obviously, this is impossible, which is why atoms could not exist if electromagnetic forces were not vastly stronger than gravity at atomic scales. The precise balance of electromagnetic forces determines the size of atoms, the energy levels of electrons, and all the chemical properties that make different elements behave in unique ways. From this perspective, gravity is not just weak at atomic scales, it is so weak as to be completely negligible. The dominance of electromagnetic forces at molecular scales explains why chemistry works the way it does. When atoms bond together to form molecules, they do so by sharing or transferring electrons through electromagnetic interactions. The strength of chemical bonds, the shapes of molecules, and the energy required for chemical reactions are all determined by electromagnetic forces acting between electrons and atomic nuclei. Gravity has no influence on these processes whatsoever. This is why chemists never need to consider gravitational effects when studying how molecules form, react, or break apart. Even in the largest molecules found in living organisms, proteins containing thousands of atoms, gravitational forces between different parts of the molecule are utterly insignificant compared to the electromagnetic forces that determine the molecule's 3-dimensional structure and chemical behavior. The electromagnetic dominance at small scales also explains many of the mechanical properties of everyday materials. When you touch a solid object and feel its resistance to your touch, you are experiencing electromagnetic repulsion between the electrons in your fingertips and the electrons in the surface of the object. The electrons do not actually come into contact. Instead, they repel each other electromagnetically when they get close enough, creating the sensation of hardness or solidity. The strength of materials, their elasticity, their thermal conductivity, and countless other properties all arise from electromagnetic interactions between atoms and molecules. Gravity contributes nothing to these properties, even though we might intuitively think that the weight of an object contributes to its structural properties. In reality, the gravitational forces within a solid object are so weak compared to electromagnetic forces that they have no measurable effect on the object's mechanical behavior. At even smaller scales, inside atomic nuclei, the strong nuclear force takes over as the dominant player. The strong force is what holds protons and neutrons together to form atomic nuclei, overcoming the tremendous electromagnetic repulsion between positively charged protons. Without the strong force, no nucleus heavier than hydrogen could exist, because the electromagnetic repulsion between protons would blow the nucleus apart instantly. The strong force is roughly 100 times more powerful than electromagnetic forces, and about 10⁻⁸ power times more powerful than gravity. However, the strong force has an extremely limited range. It only operates over distances comparable to the size of atomic nuclei, about 10⁻⁻15 meters. This short range means that the strong force has no influence on anything larger than individual atoms. which is why it does not compete with electromagnetic forces for dominance at molecular and larger scales. The weak nuclear force also operates at nuclear scales and is responsible for certain types of radioactive decay. While much weaker than the strong force, the weak force is still enormously stronger than gravity at the scales where it operates. The weak force has an even shorter range than the strong force, making it irrelevant for most everyday phenomena. But it plays a crucial role in the nuclear reactions that power stars and in the fundamental processes that govern the behavior of elementary particles. Like the strong force, the weak force's short range means that it cannot compete with electromagnetic forces for influence over atomic and molecular behavior. The mathematical reason why gravity fails to dominate at small scales lies in how gravitational force scales with the masses of the interacting objects. Gravitational force is proportional to the product of the masses involved, so as masses get smaller, gravitational forces become weaker much more rapidly than electromagnetic forces. An electron has a mass of about 9 × 10⁻31 kilograms, which is incredibly tiny. When you calculate the gravitational force between two electrons, you multiply this tiny mass by itself, giving an even tinier result. Meanwhile, the electromagnetic force between the same two electrons depends on their electric charge, which does not scale with mass in the same way. This fundamental difference in how the forces scale with the properties of particles means that gravity becomes relatively weaker and weaker as we consider smaller and smaller objects. The complete irrelevance of gravity at atomic scales has profound implications for how we understand the nature of matter. Every atom in your body, every molecule in the air you breathe, every chemical reaction that keeps you alive operates according to the laws of electromagnetic and nuclear forces alone. From the perspective of atomic physics, gravity might as well not exist. This is why the Standard Model of Particle Physics, which describes the behavior of fundamental particles and 3 of the 4 fundamental forces, treats gravity as a separate phenomenon that can be safely ignored in most calculations. The energy scales at which gravitational effects become important for individual particles are so extreme that they are far beyond anything we can currently study in laboratory experiments. Yet despite its irrelevance at small scales, gravity's weakness actually enables the complexity we see in matter at larger scales. If gravity were much stronger, it would disrupt the delicate electromagnetic balance that holds atoms together. Stronger gravitational forces could compress matter to such high densities that normal atomic structure would become impossible. The precise weakness of gravity allows electromagnetic and nuclear forces to operate freely at small scales, creating stable atoms and molecules that can then combine into larger structures. Only when enough matter accumulates do gravitational effects become significant, and by that point, the matter has already organized itself into complex arrangements determined by electromagnetic and nuclear interactions. This hierarchy of forces at different scales creates a kind of cosmic democracy where each force gets to dominate in its own domain. Gravity rules the realm of planets, stars, and galaxies. Electromagnetic forces govern atoms, molecules, and everyday materials. Strong and weak nuclear forces control the interior of atomic nuclei. This division of labor allows for incredible richness and complexity in the universe, with different physical laws becoming important at different scales. If gravity dominated at all scales, the universe would be a much simpler and less interesting place, likely consisting only of collapsed objects like black holes with no possibility for the intricate structures that make chemistry, biology, and ultimately consciousness possible. The study of why gravity does not dominate small scales has led to important insights about the fundamental nature of space and time. Einstein's general relativity shows that gravity is not really a force in the same sense as electromagnetic or nuclear forces, but rather a manifestation of the curvature of space-time itself. Mass and energy cause space-time to curve, and objects follow the straightest possible paths through this curved space-time, which we perceive as gravitational attraction. This geometric interpretation of gravity helps explain why it behaves so differently from other forces, and why it only becomes important when large amounts of mass and energy are involved. Small objects simply do not curve space-time enough to produce significant gravitational effects. The weakness of gravity at small scales also creates opportunities for testing our understanding of fundamental physics. If our theories are correct, gravitational effects should be completely negligible in atomic and molecular systems. Any detection of gravitational influences at these scales would indicate new physics beyond our current understanding. Experiments designed to look for such effects must achieve incredible precision, but they offer the possibility of discovering new fundamental forces or exotic forms of matter that could revolutionize our understanding of the universe. Modern technology relies heavily on the fact that gravity does not interfere with electromagnetic processes at small scales. Computer chips work because electrons can move through semiconductor materials according to purely electromagnetic laws, without any interference from gravitational effects. If gravity were stronger, it might disrupt the delicate electronic processes that make modern electronics possible. Similarly, chemical processes in biological systems depend on gravity being weak enough that it does not interfere with the electromagnetic forces that govern protein folding, enzyme activity, and cellular metabolism. The technological civilization we have built depends fundamentally on gravity staying in its lane and not disrupting the electromagnetic and nuclear processes that operate at smaller scales. The question of why gravity does not dominate small scales ultimately connects to some of the deepest mysteries in physics. Why are the fundamental forces so different in strength? Why does gravity seem to be special, operating through space-time curvature rather than particle exchange like the other forces? These questions drive current research in theoretical physics, from attempts to unify all forces in a single theory, to investigations of whether gravity might actually be much stronger than it appears, with most of its strength hidden in extra dimensions that we cannot directly perceive. The answers to these questions may ultimately reveal new aspects of reality that are currently beyond our imagination, but they all start with the simple observation that gravity, despite being the most familiar force in our everyday experience, is remarkably absent from the microscopic world that underlies everything we see and touch. The hierarchy problem represents one of the most profound puzzles in modern theoretical physics, a mystery that goes to the heart of why our universe has the structure it does. At its core, the hierarchy problem asks a deceptively simple question: why is gravity so incredibly much weaker than the other fundamental forces? This is not just a matter of academic curiosity. The enormous difference in strength between gravity and the electromagnetic, strong and weak forces is so extreme that it challenges our understanding of how the universe could possibly be organized this way. When physicists first began to appreciate the true magnitude of this difference, they realized they were confronting a puzzle that might hold the key to understanding the deepest nature of reality itself. The hierarchy problem forces us to ask whether there are hidden aspects of our universe that we have not yet discovered, whether our current theories are fundamentally incomplete, or whether we are missing some crucial insight that would make sense of this cosmic mystery. To understand the hierarchy problem, we need to think about what determines the strength of fundamental forces in the language of modern physics. In quantum field theory, the mathematical framework that describes 3 of the 4 fundamental forces, the strength of each force is characterized by what physicists call a coupling constant. These coupling constants are numbers that appear in the equations of physics and determine how strongly different particles interact with each other. For electromagnetic forces, the coupling constant is related to the fine structure constant, a number equal to approximately 1 divided by 137. For the strong nuclear force, the coupling constant is close to 1, indicating very strong interactions. For the weak nuclear force, the coupling constant is intermediate between electromagnetic and strong forces. But when we try to describe gravity in the same framework, we encounter something truly extraordinary. The coupling constant that would describe gravity's strength in quantum field theory is related to Newton's gravitational constant. But when expressed in the natural units that physicists use to compare fundamental forces, this coupling constant turns out to be incredibly tiny. It is approximately 10 to the minus 39th power, a number so small that it strains our ability to comprehend it. This means that gravity is not just a little bit weaker than other forces, it is weaker by a factor that has 39 zeros after the decimal point. To put this in perspective, if the strong nuclear force were represented by the height of Mount Everest, gravity would be represented by the thickness of a single sheet of paper, divided by the number of atoms in the observable universe. The sheer magnitude of this difference suggests that something very fundamental and important is happening that we do not yet understand. The hierarchy problem becomes even more puzzling when we consider the predictions of quantum field theory itself. According to our best understanding of quantum mechanics, empty space is not really empty, but is filled with quantum fluctuations, virtual particles that pop in and out of existence on incredibly short time scales. These quantum fluctuations should contribute to the effective strength of all fundamental forces, including gravity. When physicists calculate what these quantum contributions should be, they find that they should make gravity much stronger than it actually appears to be. In fact, the calculations suggest that gravity should be roughly as strong as the other fundamental forces, not weaker by 39 orders of magnitude. The fact that these calculations give completely wrong answers indicates that something crucial is missing from our understanding. This mismatch between theoretical predictions and observed reality is not just a minor discrepancy that might be resolved with better calculations. It represents a fundamental crisis in our understanding of how quantum mechanics and gravity fit together. The quantum field theory that successfully describes electromagnetic, strong, and weak forces seems to break down completely when applied to gravity. Either our understanding of quantum mechanics is incomplete, or our understanding of gravity is incomplete, or both. Some physicists have suggested that the hierarchy problem indicates that we are missing entire aspects of reality, such as extra dimensions of space or new types of particles that we have not yet discovered. One of the most important clues about the hierarchy problem comes from considering the energy scale at which quantum effects of gravity become important. This is called the Planck scale, named after Max Planck, the physicist who first discovered the fundamental quantum of action. The Planck energy is approximately 10 to the 19th power GeV, which is about 10 to the 16 power times higher than the energies we can currently achieve in particle accelerators. At this energy scale, quantum fluctuations of space-time itself become so large that our usual notions of smooth, continuous space and time break down completely. The Planck scale represents the frontier where quantum mechanics and general relativity must somehow be unified into a single, consistent theory of quantum gravity. The enormous gap between the Planck scale and the energy scales, where we observe the other fundamental forces, is itself part of the hierarchy problem. Why should there be such a vast desert of energy scales between the world we can study experimentally and the world where gravity becomes quantum mechanically important? This gap is so large that it encompasses virtually all of physics as we know it. From the lowest energy chemical reactions to the highest energy cosmic ray collisions, from the formation of atoms to the cores of neutron stars, all of these phenomena occur at energy scales that are many orders of magnitude below the Planck scale. The hierarchy problem asks why the universe is organized with such an enormous separation between the scale of quantum gravity and the scale of everything else we experience. Various theoretical approaches have been proposed to solve the hierarchy problem, each offering different insights into what might be missing from our current understanding. One class of solutions involves the idea that there are extra dimensions of space beyond the 3 dimensions we experience directly. In these theories, Gravity might actually be much stronger than it appears, but most of its strength is diluted by spreading out into these extra dimensions. From our perspective, confined to three-dimensional space, gravity appears weak because we only see a small fraction of its true strength. The other fundamental forces, in contrast, might be confined to our three-dimensional space and thus appear at full strength. This would explain why gravity seems so much weaker without requiring it to actually be fundamentally weaker. String theory, one of the most ambitious attempts to create a theory of quantum gravity, naturally incorporates extra dimensions and offers potential solutions to the hierarchy problem. In string theory, all fundamental particles are understood as different vibrational modes of tiny, one-dimensional objects called strings. The theory requires extra dimensions for mathematical consistency, and these extra dimensions could provide exactly the kind of mechanism needed to explain gravity's apparent weakness. However, string theory has not yet made definitive predictions that can be tested experimentally, so it remains unclear whether this approach will ultimately solve the hierarchy problem. Another approach to the hierarchy problem involves the idea that what we call gravity might not be a truly fundamental force, but rather an emergent phenomenon that arises from more basic interactions. Just as temperature and pressure are emergent properties that arise from the collective behavior of many molecules, gravity might emerge from the collective behavior of more fundamental degrees of freedom. In this view, the weakness of gravity would be explained by the fact that emergent forces are typically much weaker than the fundamental forces from which they arise. This idea has led to investigations of whether space-time itself might be emergent, arising from more basic quantum mechanical structures. The hierarchy problem also connects to questions about the ultimate fate and origin of our universe. If gravity were much stronger, the early universe would have evolved very differently. Stronger gravity would have caused matter to clump together much more rapidly after the Big Bang, possibly leading to a universe filled with black holes rather than the rich variety of structures we observe today. The weakness of gravity allows for the slow, gradual formation of cosmic structures over billions of years, providing time for stars to form, create heavy elements, and die, ultimately leading to the chemical complexity necessary for life. From this perspective, the hierarchy problem might be connected to the question of why our universe has properties that allow for complexity and life. Some physicists have proposed that the hierarchy problem might be solved by appealing to the anthropic principle, the idea that the fundamental constants of nature must be compatible with the existence of observers like ourselves. In this view, there might be many universes with different values of fundamental constants, but we can only exist in universes where gravity is weak enough to allow for stable atoms, long-lived stars, and gradual cosmic evolution. While this approach can explain why we observe gravity to be weak, it does not explain why such universes should exist in the first place, or why the fundamental constants should vary between different universes. Experimental efforts to probe the hierarchy problem face enormous challenges because of the vast energy scales involved. Direct tests of quantum gravity effects require energies near the Planck scale, which are completely beyond the reach of any conceivable particle accelerator. However, some theoretical models predict that signatures of extra dimensions or other solutions to the hierarchy problem might be detectable at much lower energies. Experiments at particle accelerators, like the Large Hadron Collider, have searched for evidence of extra dimensions, new particles, or other exotic phenomena that might shed light on the hierarchy problem. So far, these searches have not found clear evidence for new physics, but they have provided important constraints on possible solutions. Tests of gravity at very short distances offer another avenue for investigating the hierarchy problem. If gravity becomes stronger at short distances due to extra dimensions or other effects, This might be detectable in precision measurements of gravitational forces between small objects. These experiments require incredible precision and must carefully account for electromagnetic and other non-gravitational forces. But they offer the possibility of discovering deviations from Newton's law of gravitation that could reveal new aspects of space-time. The hierarchy problem remains one of the most important unsolved puzzles in theoretical physics, with implications that extend far beyond our understanding of gravity alone. The solution to this problem might require revolutionary new ideas about the nature of space, time, matter, and energy. It might lead to the discovery of extra dimensions, new fundamental particles, or entirely new principles that govern the behavior of the universe at its most basic level. Whatever the ultimate answer turns out to be, it will almost certainly transform our understanding of reality in ways that we cannot currently imagine. The hierarchy problem reminds us that despite the tremendous success of modern physics in explaining many aspects of the universe, there are still fundamental mysteries waiting to be solved. Mysteries that may hold the keys to understanding why our universe has the remarkable properties that make complexity, structure, and ultimately life possible. One of the most mind-bending and revolutionary ideas proposed to explain gravity's weakness involves the possibility that our familiar three-dimensional world is actually embedded in a higher dimensional reality that we cannot directly perceive. This extra dimensions hypothesis suggests that space itself has more than the three dimensions of length, width, and height that we experience in our daily lives. According to this radical idea, there might be additional spatial dimensions that are somehow hidden from our direct observation, and gravity's apparent weakness in our three-dimensional world might be explained by the fact that gravitational force can leak out into these extra dimensions, while other forces remain trapped in our familiar three-dimensional space. This concept challenges our most basic assumptions about the nature of reality and opens up possibilities for understanding the universe that are almost too strange to imagine. The mathematical foundations for extra dimensions were laid more than a century ago, long before physicists understood that gravity was unusually weak compared to other forces. In 1919, a German mathematician named Theodor Kaluza proposed that Einstein's equations of general relativity could be extended to include a fifth dimension, and that when viewed from this higher dimensional perspective, both gravity and electromagnetism emerged naturally as different aspects of the same underlying geometric structure. This was a breathtaking insight that suggested the possibility of unifying fundamental forces by considering them as manifestations of geometry in higher dimensional space. A few years later, the Swedish physicist Oskar Klein refined Kaluza's idea by proposing that the extra dimension might be curled up or compactified into a tiny circle, so small that we cannot detect it directly but large enough to influence the behavior of fundamental forces. The Kaluza-Klein idea remained largely a mathematical curiosity for decades, but it gained new relevance with the development of string theory in the 1970s and 80s. String theory requires extra dimensions for mathematical consistency. In fact, the most successful versions of string theory require a total of 10 or 11 dimensions, with 6 or 7 dimensions beyond our familiar 3 dimensions of space and 1 dimension of time. These extra dimensions must be compactified or hidden in some way to explain why we do not observe them directly, but their presence could have profound effects on the behavior of fundamental forces. In string theory, the different fundamental forces arise from different vibrational modes of tiny strings moving through this higher dimensional space, and the apparent weakness of gravity could be explained by the way gravitational effects spread out through the extra dimensions. To understand how extra dimensions could make gravity appear weak, imagine a simple analogy. Picture a garden hose viewed from a great distance. From far away, the hose appears to be a one-dimensional line, even though it actually has 3 dimensions. If you were to pour water into the hose, the water would flow not just along the length of the hose, but also around its circumference and through its interior volume. However, from a distance, you would only see the water moving along what appears to be a one-dimensional line. Similarly, if our three-dimensional world is embedded in a higher dimensional space, gravitational effects might spread out through all the available dimensions, while electromagnetic and nuclear forces might be confined to our three-dimensional slice of reality. This would make gravity appear much weaker than it really is, because we would only see the small fraction of gravitational force that operates within our three-dimensional space. The idea that gravity can access extra dimensions while other forces cannot might seem arbitrary, but there are theoretical reasons why this could happen. In many models with extra dimensions, electromagnetic and nuclear forces are carried by particles that are somehow attached to our three-dimensional space, like objects glued to the surface of a sheet of paper. These forces cannot escape into the extra dimensions because the particles that carry them are confined to our three-dimensional world. Gravity, however, might be fundamentally different. In Einstein's general relativity, gravity is not carried by particles in the same way as other forces, but is instead a manifestation of the curvature of space-time itself. If space-time has extra dimensions, then gravitational effects would naturally spread throughout all of these dimensions, diluting the apparent strength of gravity as experienced by objects confined to three-dimensional space. One of the most exciting possibilities raised by the extra dimensions hypothesis is that gravity might actually be much stronger than it appears, potentially even as strong as the other fundamental forces, with most of its strength hidden in dimensions that we cannot access. This would solve the hierarchy problem in a dramatic way, suggesting that there is no fundamental reason why gravity should be weaker than other forces. Instead, gravity only appears weak because we are seeing a dramatically weakened version of its true strength, like seeing only the shadow of a three-dimensional object cast onto a two-dimensional surface. If this idea is correct, then at very small distances, where the effects of extra dimensions might become more apparent, gravity could become much stronger than Newton's law predicts. The prospect that gravity might become stronger at small distances has inspired a new generation of precision experiments designed to test Newton's inverse square law at the shortest possible distances. These experiments look for deviations from the expected gravitational force between small objects separated by fractions of a millimeter. The technical challenges involved in these measurements are extraordinary, since gravitational forces are already incredibly weak at normal distances, and any deviation from Newton's law at short distances would be even more subtle. Experimenters must account for electromagnetic forces, surface effects, temperature variations, vibrations, and countless other sources of systematic error that could mimic or mask the signal they are looking for. The most sensitive tests of gravity at short distances involve delicate instruments called torsion balancers, modern versions of the apparatus used by Henry Cavendish more than 2 centuries ago to make the first measurement of Newton's gravitational constant. These modern torsion balancers can detect forces as small as 10 to the -18 newtons, which is roughly equivalent to the gravitational attraction between a grape and a bacterium. The experiments involve measuring the gravitational force between carefully machined metal objects, as their separation is varied from distances of several millimeters down to distances smaller than the width of a human hair. Any deviation from Newton's inverse square law at these small distances could indicate the presence of extra dimensions or other exotic physics. So far, these precision tests have not found clear evidence for deviations from Newton's law of gravitation, but they have provided important constraints on possible extra-dimensional models. The results show that if extra dimensions exist, they must be smaller than about 1/10 of a millimeter, or else their effects would have been detected in these experiments. This places strong limits on certain types of extra-dimensional theories. but it does not rule out the possibility that extra dimensions exist at even smaller scales. The search continues with ever more sensitive experiments and more sophisticated techniques for isolating gravitational effects from other sources of systematic error. Theoretical models with extra dimensions make specific predictions about how gravity should behave at small distances, and these predictions depend on the number of extra dimensions and their size. In some models, gravity should become stronger as an inverse fourth power or inverse fifth power law instead of the familiar inverse square law, reflecting the spreading of gravitational effects through 4 or 5 total spatial dimensions instead of 3. Other models predict more complex behavior, with oscillations or other features in the gravitational force at specific distance scales related to the size and shape of the extra dimensions. The diversity of possible predictions means that precision tests of gravity can potentially distinguish between different theoretical models and provide clues about the nature of any hidden dimensions. The extra dimensions hypothesis also has implications for high-energy particle physics experiments. If extra dimensions exist, high-energy collisions between particles might produce gravitational effects that are much stronger than expected based on ordinary three-dimensional gravity. Some theoretical models predict that miniature black holes could be created in particle colliders if gravity becomes strong enough at small distances due to extra dimensions. These black holes would be incredibly tiny and would evaporate almost instantaneously due to Hawking radiation, but their creation and decay might produce detectable signatures in particle detector experiments. Searches for such exotic phenomena have been carried out at the Large Hadron Collider and other high-energy facilities, though no clear evidence for extra-dimensional effects has been found so far. Another potential signature of extra dimensions involves the behavior of gravitons, the hypothetical particles that would carry gravitational force in a quantum theory of gravity. If extra dimensions exist, gravitons created in high-energy particle collisions might escape into the extra dimensions, carrying away energy and momentum that would be undetectable in our three-dimensional world. This would appear as missing energy in particle collision experiments, similar to the signature expected from other exotic particles like neutrinos that interact very weakly with ordinary matter. Experimental searches for missing energy signatures that could indicate graviton production have been conducted, but the results have been consistent with expectations from known physics rather than exotic extra-dimensional effects. The mathematical description of extra dimensions involves some of the most advanced concepts in modern theoretical physics. The extra dimensions cannot simply be infinite in extent like our familiar 3 dimensions, because if they were, we would certainly have noticed their effects by now. Instead, the extra dimensions must be compactified, meaning they are curled up or folded in such a way that they have a finite size, typically much smaller than anything we can directly observe. The geometry of these compactified dimensions can be incredibly complex, involving mathematical structures called Calabi-Yau manifolds, or other exotic geometrical objects that exist only in higher dimensional mathematics. The way that extra dimensions are compactified determines many of the observable properties of fundamental forces in our three-dimensional world. Different compactification schemes can lead to different numbers of particle types, different force strengths, and different symmetries in the laws of physics. This suggests that the fundamental constants of nature, including the strength of gravity relative to other forces, might be determined by the geometric properties of hidden extra dimensions. If this is true, then understanding why gravity is so weak would require understanding the detailed geometry of spaces that we cannot directly observe, a challenge that pushes the boundaries of both theoretical physics and pure mathematics. String theory provides the most developed framework for thinking about extra dimensions and their effects on fundamental forces. In string theory, the extra dimensions are not just mathematical abstractions, but are thought to be real, physical aspects of spacetime that determine the properties of all fundamental particles and forces. The vibrational modes of strings moving through these extra dimensions correspond to different types of particles, and the geometry of the extra dimensions determines which particles can exist and how they interact with each other. This suggests a deep connection between the large-scale structure of the universe and the microscopic properties of matter, mediated by the hidden geometry of extra-dimensional space. Recent developments in theoretical physics have led to even more exotic ideas about extra dimensions and their role in determining the strength of gravity. Some models propose that our entire three-dimensional world might be a membrane or brane floating in a higher dimensional space, with gravity able to propagate throughout the higher dimensional bulk, while other forces are confined to the brane. Other models suggest that extra dimensions might not be static, but could be dynamically evolving, possibly explaining not just the weakness of gravity, but also the accelerating expansion of the universe attributed to dark energy. These ideas remain highly speculative, but they illustrate the rich possibilities that emerge when we take seriously the idea that reality might have more dimensions than we directly experience. The extra dimensions hypothesis represents one of the most ambitious attempts to solve the mystery of gravity's weakness, but it also raises new questions that are equally challenging. If extra dimensions exist, why are they hidden from us? What determines their size and shape? Could we ever find a way to directly access or manipulate these hidden dimensions? The answers to these questions might revolutionize not just our understanding of gravity, but our entire conception of space, time, and the fundamental structure of reality. Whether or not extra dimensions ultimately provide the correct explanation for gravity's weakness, the search for them has already led to new experimental techniques, new mathematical insights, and new ways of thinking about the deepest questions in physics. While we have spent considerable time exploring gravity's weakness at small scales, it is crucial to understand that gravity is not universally weak throughout the universe. There are domains where gravity transforms from the feeble force we experience in our daily lives into the dominant architect of cosmic structure, the force that shapes everything from the formation of stars to the large-scale organization of matter across billions of light years. This transformation happens not because gravity itself becomes stronger, but because the other fundamental forces, which dominate at small scales, either cancel out or become irrelevant when we consider sufficiently large amounts of matter and sufficiently vast distances. Understanding where and why gravity takes control reveals fundamental insights about how our universe is organized and why it has the rich, complex structure we observe today. The key to gravity's cosmic dominance lies in its unique characteristics among the fundamental forces. While electromagnetic forces can be both attractive and repulsive, gravity is purely attractive. There is no such thing as negative mass that could create gravitational repulsion to cancel out gravitational attraction. This means that as more and more matter accumulates in a region of space, gravitational effects always add up in the same direction, steadily increasing the total gravitational influence. Electromagnetic forces, by contrast, tend to cancel out in large accumulations of matter because atoms and molecules typically contain equal numbers of positive and negative charges. When billions upon billions of atoms come together to form a planet or star, their individual electromagnetic fields largely neutralize each other, leaving only a tiny net electromagnetic effect. But every atom contributes its full gravitational influence to the total, creating an ever-growing gravitational field as matter accumulates. This accumulation effect becomes dramatically apparent when we consider astronomical objects. A single hydrogen atom produces a gravitational field so weak that it is utterly negligible for any practical purpose. But when 10 to the 57 hydrogen atoms come together to form a star like our Sun, their combined gravitational influence becomes powerful enough to compress matter to densities and temperatures where nuclear fusion can occur. The gravitational field of the Sun is strong enough to hold planets in orbit across distances of billions of kilometers and to influence the motion of comets at the very edges of the solar system. This represents an enormous amplification of gravitational effects through the simple process of accumulating vast amounts of matter in one location. The Sun's gravitational dominance over the solar system illustrates how gravity takes control at astronomical scales. The electromagnetic forces between the Sun and Earth are essentially zero because both objects are electrically neutral on large scales. The strong and weak nuclear forces have ranges so short that they cannot reach beyond the objects where they operate. Only gravity can reach across the 150 million kilometers that separate Earth from the Sun and maintain the delicate balance that keeps our planet in a stable orbit. Without gravity's long-range attractive force, there would be no solar systems, no planetary orbits, and no stable configurations of matter at astronomical distances. At even larger scales, gravity's dominance becomes even more pronounced. Galaxies like our Milky Way contain hundreds of billions of stars, each contributing its gravitational influence to the total gravitational field of the galaxy. The combined gravitational effect is so powerful that it can hold the entire galactic structure together for billions of years, maintaining the spiral arms and central bulge that give galaxies their characteristic shapes. The rotation curves of galaxies, which show how fast stars orbit around galactic centers at different distances, are determined almost entirely by gravitational forces. Other forces are simply irrelevant at the scale of galactic dynamics, having either cancelled out or become too weak to influence the motion of objects separated by tens of thousands of light years. The discovery of galaxy clusters and superclusters has revealed gravity's influence operating on even more impressive scales. Galaxy clusters can contain thousands of individual galaxies, each containing billions of stars, all held together by their mutual gravitational attraction. The gravitational fields of these clusters are so strong that they can bend the path of light itself, a phenomenon called gravitational lensing that allows astronomers to study the distribution of matter in the universe. Some galaxy clusters act like enormous cosmic magnifying glasses, using their gravitational fields to focus and amplify light from even more distant galaxies, allowing us to see objects that would otherwise be too faint to detect. The large-scale structure of the universe, often called the cosmic web, represents gravity operating at its most impressive scale. Observations of the distribution of galaxies across billions of light years reveal a vast network of filaments, walls, and voids that spans the observable universe. This cosmic web is thought to be the result of gravitational amplification of tiny density fluctuations that existed in the early universe. Over billions of years, gravity gradually pulled matter together along these filaments, creating the spectacular large-scale structure we observe today. At these scales, gravity is not just dominant, but essentially the only force that matters for determining how matter is distributed throughout the cosmos. The formation of cosmic structure through gravitational collapse is one of the most important processes in the universe's evolution. In the early universe, shortly after the Big Bang, matter was distributed almost uniformly throughout space, with only tiny variations in density from place to place. These small density fluctuations, probably created by quantum mechanical processes during cosmic inflation, provided the seeds for all future structure formation. Regions that were slightly denser than average had slightly stronger gravitational fields, which attracted surrounding matter and made them even denser. This created a positive feedback process where dense regions became denser and sparse regions became sparser, eventually leading to the formation of the first stars, galaxies, and larger structures. The timescales involved in gravitational structure formation reveal another important aspect of gravity's cosmic role. While electromagnetic and nuclear forces operate on timescales ranging from fractions of a second to millions of years, gravitational processes often unfold over hundreds of millions or billions of years. The formation of a galaxy cluster from initial density fluctuations takes several billion years, during which gravity slowly and steadily pulls matter together across vast distances. This slow pace of gravitational evolution is actually crucial for the development of complexity in the universe. If gravity were much stronger, structures would form so quickly that there would be no time for the gradual processes that lead to star formation, planetary systems, and ultimately the conditions necessary for life. The role of dark matter in cosmic structure formation highlights gravity's importance in ways that were not anticipated by early theories. Dark matter, which makes up approximately 85% of all matter in the universe, interacts gravitationally, but not electromagnetically. This means that dark matter responds only to gravitational forces and is invisible to light and other electromagnetic radiation. The fact that dark matter dominates the matter content of the universe makes gravity even more important for large-scale structure formation. Dark matter halos provide the gravitational scaffolding around which normal matter can condense to form stars and galaxies. Without dark matter's gravitational influence, the universe would look very different, with much less structure and probably no galaxies at all. Neutron stars represent an extreme example of gravity's power when enormous amounts of matter are compressed into a small volume. These objects, which form when massive stars collapse at the end of their lives, pack as much mass as the Sun into a sphere only about 20 kilometers across. The gravitational field at the surface of a neutron star is so strong that it can bend light by measurable amounts and create time dilation effects, where time passes more slowly than it does in weaker gravitational fields. The matter inside neutron stars is compressed to densities comparable to atomic nuclei, creating conditions where gravitational forces overwhelm even the strong nuclear force that normally keeps protons and neutrons from overlapping. Black holes represent the ultimate triumph of gravity over all other forces. When enough matter accumulates in a small enough region, gravitational forces become so strong that nothing, not even light, can escape from within a certain distance called the event horizon. Inside a black hole, gravity completely dominates all other physical processes, crushing matter to infinite density at the central singularity according to our current understanding of physics. The formation of black holes demonstrates that there is no upper limit to gravity's strength given sufficient mass and density. While gravity appears weak in our everyday experience, it has the potential to become arbitrarily strong under the right conditions. The recent detection of gravitational waves has provided new insights into gravity's behavior in extreme environments. When two black holes or neutron stars spiral into each other and merge, they create ripples in space-time itself that propagate outward at the speed of light. These gravitational waves carry information about some of the most violent and energetic processes in the universe, events where gravity's effects are so strong that they literally shake the fabric of space-time. The ability to detect these waves has opened up an entirely new way of studying the universe and has confirmed many predictions of Einstein's general relativity in regimes where gravitational effects are extremely strong. The cosmic microwave background radiation, the afterglow of the Big Bang, provides evidence for gravity's role in shaping the universe from its earliest moments. Tiny temperature fluctuations in this radiation, measured by satellites like Planck and WMAP, reflect density variations in the early universe that would later grow under gravitational amplification to form galaxies and larger structures. The pattern of these fluctuations encodes information about the fundamental properties of the universe, including the relative amounts of normal matter, dark matter, and dark energy. The fact that we can read the universe's history in these temperature variations demonstrates gravity's fundamental role in cosmic evolution. Dark energy, the mysterious force causing the universe's expansion to accelerate, represents a cosmic scale phenomenon where gravity meets its match. While gravity tries to pull matter together and slow down cosmic expansion, dark energy appears to have the opposite effect, driving space itself to expand at an ever-increasing rate. The competition between gravity and dark energy determines the ultimate fate of the universe. If gravity eventually wins, the universe might recollapse in a big crunch. If dark energy continues to dominate, the universe will expand forever, with galaxies moving apart until stars burn out and black holes evaporate. This cosmic battle between gravity and dark energy is being fought on the largest possible scales, with the destiny of everything in the universe hanging in the balance. The study of cosmic structure formation has revealed that gravity's weakness at small scales is actually essential for the universe's complexity. If gravity were much stronger, it would have prevented the formation of stable atoms and molecules by disrupting electromagnetic bonds. If it were much weaker, matter would never have clumped together enough to form stars and galaxies. The precise strength of gravity appears to be finely tuned to allow for both atomic stability at small scales and structure formation at large scales. This balance enables the universe to support both the complex chemistry necessary for life and the large-scale structures that provide stable environments where life can evolve. The realization that gravity is not weak everywhere but becomes dominant at large scales has profound implications for our understanding of the universe's organization. It suggests that the universe operates according to a kind of cosmic hierarchy, where different forces control different scales of structure. This hierarchy allows for incredible richness and complexity, with intricate phenomena occurring at every level, from subatomic particles to galaxy clusters. Gravity's role as the architect of large-scale structure makes it arguably the most important force for determining the overall character and evolution of the universe, despite its apparent weakness in our everyday experience. Understanding this cosmic hierarchy and gravity's central role within it continues to drive research in cosmology and astrophysics, as scientists work to unravel the mysteries of how our complex and beautiful universe came to be. Deep within the mathematical foundations of physics lies a set of fundamental scales that represent the absolute limits of our physical theories and perhaps the boundaries of reality itself. These are called the Planck scales, named after Max Planck, the German physicist who first recognized their significance in the early 20th century. The Planck scales define the regime where quantum mechanics and general relativity, our two most successful theories of physics, must somehow merge into a unified description of nature. At these scales, our usual concepts of space, time, matter, and energy break down completely, replaced by a quantum foam of space-time, where the very notion of smooth, continuous geometry becomes meaningless. Understanding the Planck scales is crucial for grasping why gravity appears so weak in our everyday world, because these scales reveal that gravity's apparent weakness might be nothing more than an illusion created by our limited perspective on the true nature of reality. The Planck length, approximately 1.6 times 10 to the minus 35 meters, represents the smallest distance that has any physical meaning according to our current understanding of physics. To appreciate just how incredibly tiny this distance is, consider that the Planck length is smaller than a proton by the same factor that a proton is smaller than a human being. If a proton were scaled up to the size of the observable universe, the Planck length would still be smaller than a single atom. At distances shorter than the Planck length, quantum fluctuations of space-time itself become so violent that the very concept of distance loses its meaning. Space and time, instead of being smooth and continuous as they appear at larger scales, become a churning quantum foam where virtual black holes constantly appear and disappear, where the geometry of space-time fluctuates wildly from moment to moment. The Planck time, about 5.4 times 10 to the minus 44 seconds, represents the shortest interval of time that can have physical significance. This is the time it would take light to travel one Planck length, and it represents the fundamental limit on how finely we can divide time into meaningful intervals. Events that occur on timescales shorter than the Planck time cannot be distinguished from each other using any conceivable physical process. The Planck time is so short that more Planck time intervals occur in a single second than seconds have occurred since the Big Bang began nearly 14 billion years ago. At the Planck timescale, our normal concepts of causality, where effects follow causes in a well-defined temporal sequence, may break down completely as quantum uncertainty makes it impossible to determine the order of events. The Planck mass, approximately 2.2 times 10 to the minus 8 kilograms, might seem large compared to the Planck length and time, but it represents something equally fundamental. The Planck mass is the mass of a hypothetical particle whose Compton wavelength, a quantum mechanical property related to its wave nature, would equal the Planck length. Such a particle would represent the ultimate fusion of quantum mechanics and gravity, a quantum gravitational object where both quantum effects and gravitational effects are equally important. While no such particle has ever been observed, and it is unclear whether such particles could even exist in nature, the Planck mass provides a natural scale for thinking about quantum gravity phenomena. The Planck energy, which corresponds to the energy equivalent of the Planck mass according to Einstein's famous equation E equals mc squared, is approximately 1.2 times 10 to the 19th GeV. This energy is almost unimaginably large on the scale of particle physics. The most powerful particle accelerator ever built, the Large Hadron Collider, can accelerate particles to energies of about 14 TeV, which is 10 to the 15th power times smaller than the Planck energy. To reach Planck scale energies, we would need a particle accelerator roughly the size of our galaxy. The Planck energy represents the scale at which individual particles would have gravitational fields so strong that they would collapse into black holes, merging the quantum world of particles with the gravitational world of space-time curvature. The significance of the Planck scales for understanding gravity's weakness lies in the fact that they represent the natural energy scale, where gravitational interactions become as strong as other fundamental forces. At everyday energy scales, far below the Planck scale, gravity appears weak because we are comparing it to other forces at energy scales, where gravity is not meant to be strong. It is like judging the strength of a giant by watching how it interacts with ants. The giant appears weak because the scale of interaction is inappropriate for revealing its true strength. Similarly, gravity appears weak at atomic and molecular scales because these scales are enormously far from the Planck scale where gravity's true strength would be revealed. This perspective suggests that gravity's apparent weakness might be nothing more than an artifact of the energy scales at which we typically study physics. If we could somehow probe physics at Planck scale energies, gravity might appear just as strong as electromagnetic, strong and weak nuclear forces. The hierarchy problem, which asks why gravity is so much weaker than other forces, might be resolved simply by recognizing that we are asking the wrong question. Instead of asking why gravity is weak, we should perhaps ask why the energy scales of everyday physics are so much smaller than the Planck scale, or why other forces remain strong even at low energies, while gravity becomes weak. The concept of running coupling constants in quantum field theory provides another perspective on how force strengths depend on the energy scale at which they are measured. In quantum field theory, the apparent strength of fundamental forces changes as we probe them at different energy scales due to quantum mechanical effects involving virtual particles. These changes are described by equations called renormalization group equations, which show how coupling constants run or evolve with energy. For the electromagnetic, strong and weak forces, experiments have confirmed that their strengths do indeed change with energy in the ways predicted by quantum field theory. The electromagnetic force becomes stronger at higher energies, while the strong force becomes weaker, and the weak force strength also changes in characteristic ways. If gravity could be described by a similar quantum field theory, its strength would also run with energy, potentially becoming much stronger at higher energy scales. Some theoretical models suggest that all fundamental forces, including gravity, might converge to similar strengths at extremely high energies near the Planck scale. This would represent a grand unification of all forces, where the apparent differences between electromagnetic, strong, weak, and gravitational interactions would be revealed as low-energy artifacts of a more fundamental unified theory. Such a unification would explain gravity's weakness not as a fundamental property, but as a consequence of the particular energy scales at which we happen to live and conduct experiments. The role of the Planck scale in quantum gravity theories provides additional insights into gravity's apparent weakness. String theory, loop quantum gravity, and other approaches to quantum gravity all suggest that spacetime itself has a discrete quantum mechanical structure at the Planck scale. In these theories, smooth spacetime is an emergent property that only appears when we average over many Planck scale quantum fluctuations, much like the smooth surface of a lake emerges when we average over many microscopic water molecules. The gravitational force that we experience might be an emergent phenomenon that arises from more fundamental quantum mechanical processes operating at the Planck scale. If gravity is indeed emergent rather than fundamental, this could explain why it appears so different from other forces and why it seems so much weaker at macroscopic scales. Emergent phenomena are typically much weaker than the fundamental interactions from which they arise, just as the pressure exerted by a gas is much weaker than the electromagnetic forces between individual molecules. The weakness of gravity might simply reflect the fact that it is a collective, statistical effect arising from an enormous number of Planck-scale quantum processes, while electromagnetic and nuclear forces are more direct manifestations of fundamental quantum field interactions. Black hole thermodynamics provides compelling evidence for the fundamental role of the Planck scale in gravitational physics. Stephen Hawking's discovery that black holes have temperature and entropy revealed deep connections between gravity, quantum mechanics, and thermodynamics. The temperature of a black hole is inversely proportional to its mass, which means that black holes with masses comparable to the Planck mass would have temperatures comparable to the Planck temperature, about 10 to the 32nd power Kelvin. Such black holes would be in thermal equilibrium with their own Hawking radiation, representing a kind of fundamental quantum gravitational object where all the Planck scales come together in a unified description. The holographic principle, which emerged from studies of black hole thermodynamics, suggests that all the information contained within a region of space can be encoded on its boundary, much like a hologram encodes three-dimensional information on a two-dimensional surface. This principle implies that gravity in three-dimensional space might be equivalent to a quantum field theory, operating on the two-dimensional boundary of that space. If true, this would mean that gravity is not really a force operating in three-dimensional space at all, but rather a kind of projection or shadow of quantum mechanical processes occurring on a lower dimensional boundary. This radical reinterpretation of gravity could explain its apparent weakness as a consequence of its fundamentally holographic nature. The ADS-CFT correspondence, one of the most important developments in theoretical physics over the past few decades, provides a concrete example of how gravity in a higher dimensional space can be equivalent to a quantum field theory without gravity in a lower dimensional space. ADS-CFT stands for Anti-de Sitter Space Conformal Field Theory Correspondence, and it shows that certain gravitational theories in spaces with extra dimensions are mathematically equivalent to non-gravitational quantum field theories in spaces with fewer dimensions. This correspondence suggests that gravity might not be a fundamental force at all, but rather an emergent phenomenon that arises when we view certain quantum field theories from a higher dimensional perspective. Experimental approaches to probing physics near the Planck scale face seemingly insurmountable challenges, but theoretical investigations continue to provide new insights. The energies required to directly study Planck scale physics are so enormous that no conceivable technology could achieve them. However, cosmological observations of the early universe, studies of black hole evaporation, and precision tests of general relativity might provide indirect windows into Planck scale physics. The cosmic microwave background radiation, for example, might contain subtle signatures of quantum gravitational effects that occurred during cosmic inflation in the very early universe. Gravitational wave detectors might eventually become sensitive enough to detect the stochastic background of gravitational waves that could be produced by Planck scale quantum fluctuations. The connection between the Planck scale and gravity's apparent weakness has profound implications for our understanding of the fundamental structure of reality. It suggests that our everyday experience of physics, where gravity appears weak and space-time appears smooth and continuous, might be a kind of low-energy approximation to a much richer and stranger underlying reality. At the Planck scale, the familiar concepts of particles, forces, space, and time might all be replaced by more fundamental, quantum mechanical degrees of freedom that we do not yet understand. The apparent weakness of gravity might be telling us that we live in a kind of classical shadow of a fundamentally quantum universe, where the true nature of reality only becomes apparent at energy scales far beyond our current experimental reach. The search for a theory of quantum gravity that can describe physics at the Planck scale represents one of the greatest challenges in modern theoretical physics. Such a theory would need to unify general relativity and quantum mechanics, potentially explaining not only why gravity appears weak, but also resolving paradoxes like the information loss problem in black holes and the nature of cosmological singularities. The ultimate theory might reveal that gravity's weakness is just one aspect of a much larger story about how quantum mechanics and space-time are related at the deepest level. Recent developments in quantum information theory have suggested new ways of thinking about the relationship between quantum mechanics and gravity at the Planck scale. The idea that space-time itself might be built from quantum entanglement, with the geometry of space emerging from the pattern of quantum correlations between microscopic degrees of freedom, offers a radically new perspective on gravity's fundamental nature. If space-time is indeed emergent from quantum entanglement, then gravity's apparent weakness might reflect the fact that we are seeing only a coarse-grained, macroscopic approximation to the underlying quantum structure of reality. The Planck scale connection ultimately suggests that gravity's weakness is not a fundamental mystery, but rather a clue pointing toward a deeper understanding of how quantum mechanics and gravity fit together. The resolution of this mystery might require us to abandon our classical notions of space, time, and force in favor of a more fundamental quantum mechanical description of reality. When we finally achieve this deeper understanding, gravity's apparent weakness might be revealed as one of the most important clues that led us to discover the true quantum nature of space-time itself. One of the most profound questions we can ask about gravity's weakness is whether this weakness is a permanent, unchanging feature of our universe, or whether gravity's strength might vary over time, space, or under different physical conditions. This question touches on some of the deepest issues in cosmology and fundamental physics, challenging our assumptions about the constancy of nature's laws and opening up possibilities for understanding why our universe has the particular properties we observe. The idea that fundamental constants might not be truly constant has a long and distinguished history in physics, dating back to early speculations by Paul Dirac in the 1930s about whether the gravitational constant might change as the universe ages. Today, this question has evolved into sophisticated theoretical models and precision experimental tests that probe whether gravity's strength has remained the same throughout cosmic history. The theoretical motivation for considering variable gravity comes from several different directions in modern physics. Some cosmological models suggest that the fundamental constants of nature, including Newton's gravitational constant g, might evolve as the universe expands and cools. These models often arise from attempts to solve problems in cosmology, such as the flatness problem, the horizon problem, and the cosmological constant problem. In scalar tensor theories of gravity, which include an additional scalar field beyond the metric tensor of general relativity, the effective strength of gravitational interactions can depend on the value of this scalar field, which might change over time as the universe evolves. String theory and other approaches to quantum gravity also suggest mechanisms by which fundamental constants could vary, either gradually over cosmic time or in response to changes in the geometry of extra dimensions. One of the most intriguing theoretical possibilities is that gravity's strength might have been different in the early universe compared to its current value. Some inflationary cosmology models propose that during the rapid expansion phase that occurred in the first fraction of a second after the Big Bang, the effective strength of gravity might have been much different from its present-day value. This could help explain certain features of the cosmic microwave background radiation and the large-scale structure of the universe that are difficult to account for with constant fundamental constants. If gravity was stronger in the early universe, it might have helped to amplify the tiny quantum fluctuations that eventually grew into galaxies and galaxy clusters, providing a natural explanation for the observed patterns in cosmic structure. The possibility that gravity's strength could change also arises in theories that attempt to explain the acceleration of cosmic expansion attributed to dark energy. Some modified gravity theories propose that the apparent acceleration is not due to a mysterious dark energy component, but rather to changes in the nature of gravity itself on cosmological scales. In these theories, gravity might become weaker at very large distances or very low densities, reducing its ability to slow down cosmic expansion and creating the appearance of accelerated expansion. If such modifications to gravity exist, they would represent a fundamental change in our understanding of how gravity behaves under different conditions. Experimental tests of whether gravity's strength has changed over time require incredibly precise measurements and clever indirect approaches, since we cannot directly measure Newton's gravitational constant in the distant past. One of the most powerful methods involves studying the orbital decay of binary pulsar systems. Pulsars are rapidly rotating neutron stars that emit beams of radio waves like cosmic lighthouses. When two pulsars orbit each other in a binary system, they gradually spiral inward due to energy loss from gravitational wave emission, as predicted by Einstein's general relativity. The rate of this orbital decay depends on the strength of gravity, so precise timing measurements of binary pulsars over many years can test whether G has changed during the observation period. The Hulse-Taylor binary pulsar, discovered in 1974, provided the first precision test of gravitational wave emission and has been monitored for decades to look for changes in gravity's strength. The orbital period of this system decreases by about 75 microseconds per year due to gravitational wave energy loss, exactly as predicted by general relativity, assuming a constant gravitational constant. Any significant change in G over the observation period would show up as a deviation from the predicted orbital decay rate. Similar measurements have been made for other binary pulsar systems, providing constraints on how much the gravitational constant could have changed over the past few decades. Ancient solar eclipse records provide another window into gravity's historical strength. Total solar eclipses occur when the moon passes directly between Earth and the Sun, casting a shadow on Earth's surface. The precise timing and location of these eclipses depends on the orbital dynamics of the Earth-Moon system, which in turn depends on the strength of gravity. Historical records of solar eclipses, some dating back thousands of years, can be compared with calculations based on current orbital parameters to look for discrepancies that might indicate changes in gravitational strength. However, these measurements are complicated by other effects such as tidal friction that also cause changes in Earth's rotation and the Moon's orbit over long time periods. geological and paleontological evidence has been used to investigate whether gravity's strength might have changed over much longer timescales. Some researchers have examined growth patterns in ancient corals and other organisms that might be sensitive to changes in Earth's gravitational field. Others have looked at the structure of ancient tidal deposits or the dynamics of ancient impact craters for clues about past gravitational strength. However, these geological approaches face significant challenges in separating potential gravitational effects from the many other geological and biological processes that can influence the phenomena being studied. Big Bang nucleosynthesis, the process by which light elements like hydrogen, helium, and lithium were formed in the first few minutes after the Big Bang, provides one of the most sensitive tests of whether fundamental constants were different in the early universe. The abundances of these elements depend critically on the expansion rate of the early universe, which in turn depends on the strength of gravity through Einstein's field equations. Observations of the cosmic abundances of light elements can be compared with theoretical calculations to constrain how much the gravitational constant could have differed from its present value during the first few minutes of cosmic history. These studies suggest that if gravity's strength was different during Big Bang nucleosynthesis, the difference could not have been more than a few percent. The cosmic microwave background radiation offers another probe of gravity's strength in the early universe. The pattern of temperature fluctuations in this radiation reflects the acoustic oscillations of matter and radiation in the early universe, driven by the competition between gravitational attraction and radiation pressure. The detailed characteristics of these oscillations depend on fundamental constants, including the gravitational constant. Precise measurements by satellites like Planck and WMAP have provided constraints on possible variations in gravity's strength during the era when the cosmic microwave background was formed, about 380,000 years after the Big Bang. Laboratory measurements of Newton's gravitational constant over time provide the most direct test of whether G is changing in the present epoch. However, these measurements are extraordinarily challenging because gravitational forces are so weak, and because many systematic effects can mimic or mask genuine changes in the gravitational constant. Different experimental groups have sometimes obtained slightly different values for G, leading to ongoing debates about whether these differences reflect systematic errors or genuine temporal variations. The most precise measurements suggest that if G is changing at all, the rate of change must be less than 1 part in 10 to the 13th power per year, an incredibly small effect that pushes the limits of experimental precision. Lunar laser ranging experiments provide another precise test of gravitational constancy. Since the Apollo missions placed retroreflectors on the Moon's surface, scientists have been able to measure the Earth-Moon distance with millimeter precision by timing laser pulses bounced off these retroreflectors. Any change in the gravitational constant would affect the Moon's orbital motion and show up as a systematic change in the Earth-Moon distance over time. Decades of lunar laser ranging data have provided some of the most stringent constraints on possible changes in G, limiting any rate of change to less than 1 part in 10 to the 13th power per year. The theoretical implications of a changing gravitational constant would be profound for our understanding of physics and cosmology. If fundamental constants can change, it suggests that they are not truly fundamental, but rather are determined by some deeper, more dynamic aspects of physics that we do not yet understand. This could point toward theories with extra dimensions, where the apparent values of fundamental constants in our three-dimensional world depend on the size and shape of the extra dimensions, which might themselves evolve over time. Alternatively, changing constants might indicate the presence of new fields or particles that couple to gravity and influence its apparent strength. Some theories propose that multiple universes with different values of fundamental constants might exist simultaneously, with observers like ourselves naturally finding ourselves in universes where the constants have values compatible with the existence of complexity and life. In this multiverse scenario, the question of why gravity has its particular strength in our universe would be answered by the anthropic principle. We observe gravity to be weak because we can only exist in universes where gravity is weak enough to allow for stable atoms, long-lived stars, and gradual structure formation. However, this approach raises new questions about the mechanism that could generate multiple universes with different physical laws, and about whether such theories can make testable predictions. The search for varying fundamental constants has also led to investigations of whether other aspects of gravity besides its overall strength might change over time or space. Some theories suggest that the speed of gravitational waves, the number of polarization states of gravitons, or the range of gravitational interactions might vary under different conditions. Tests of these ideas require extremely sensitive experiments and careful analysis to distinguish genuine variations from systematic effects or observational errors. Recent developments in gravitational wave astronomy have opened up new possibilities for testing the constancy of gravity's properties. The Laser Interferometer, Gravitational Wave Observatory, LIGO, and its international partners have detected gravitational waves from merging black holes and neutron stars, providing direct observations of gravity in its strongest regimes. These observations can test whether gravity behaves exactly as predicted by general relativity, or whether there are deviations that might indicate modifications to gravitational physics. Future gravitational wave detectors will be even more sensitive and may be able to detect subtle effects that could reveal variations in gravitational parameters. The possibility that gravity's strength could change also connects to ongoing mysteries about dark matter and dark energy. Some researchers have proposed that what we interpret as dark matter might actually be evidence for modifications to gravity that occur under certain conditions, such as very low accelerations or very large length scales. Similarly, the accelerating expansion attributed to dark energy might reflect changes in gravity's behavior rather than the existence of a new form of energy. Testing these ideas requires careful comparison of observations with predictions from modified gravity theories and conventional general relativity with dark matter and dark energy. Precision tests of the equivalence principle, which states that gravitational and inertial mass are exactly equal, provide another avenue for investigating possible changes in gravity's nature. If the gravitational constant or other aspects of gravity were changing, different materials might respond differently to gravitational fields, violating the equivalence principle. Experiments using torsion balances, falling corner cubes, and orbiting test masses have tested the equivalence principle to extraordinary precision, looking for any indication that different materials experience slightly different gravitational forces. The study of whether gravity's strength can change ultimately addresses fundamental questions about the nature of physical law itself. Are the laws of physics truly universal and eternal? Or are they more like local bylaws that can vary from place to place and time to time? The answer to this question will help determine whether we live in a universe governed by fixed mathematical laws or in a more dynamic reality where the rules themselves can evolve. As our experimental techniques become more sophisticated and our theoretical understanding deepens, we may finally be able to answer whether gravity's puzzling weakness is a permanent feature of our universe or just a temporary phase in its cosmic evolution. The implications of this answer will reach far beyond our understanding of gravity alone, potentially revolutionizing our conception of the fundamental nature of reality itself. As we reach the end of our journey through the mystery of gravity's weakness, we find ourselves with a profound new appreciation for this most familiar yet most enigmatic of forces. What began as a simple question about why a tiny magnet can overcome the gravitational pull of an entire planet has led us through some of the deepest and most beautiful ideas in modern physics. We have discovered that gravity's apparent weakness is not a flaw in the cosmic design, but rather one of the most essential features that makes our universe capable of supporting the rich complexity we see around us. From the intricate dance of electrons in atoms, to the majestic spiral arms of galaxies stretching across millions of light years. Gravity's weakness is what allows stars to live long enough for life to evolve. If gravity was significantly stronger, stars would burn through their nuclear fuel so rapidly that they would exhaust themselves in millions of years rather than billions, leaving no time for the slow processes of planetary formation, chemical evolution, and biological development that ultimately led to our existence. The delicate balance between gravity's attractive pull and the outward pressure from nuclear fusion in stellar cores creates a cosmic timekeeper that regulates the pace of cosmic evolution. Stronger gravity would accelerate this cosmic clock beyond the point where complexity could emerge, while weaker gravity would slow it down so much that stars might never ignite at all. The weakness of gravity also enables the formation of stable planetary systems where life can flourish over geological timescales. The orbits of planets around stars represent a precise balance between gravitational attraction and orbital motion that can persist for billions of years with only tiny changes. This orbital stability provides the steady, predictable environments that life requires to evolve from simple chemical reactions to complex ecosystems. If gravity were much stronger, planetary orbits would decay rapidly as planets spiraled into their stars. If it were much weaker, planets would drift away from their stars, leaving them cold and lifeless in the darkness of interstellar space. Perhaps most remarkably, gravity's weakness allows galaxies to form slowly and maintain their structure for billions of years, creating the large-scale cosmic architecture that provides stable environments for star formation and planetary development. The slow accumulation of matter under gravity's gentle influence creates the conditions where successive generations of stars can form, live, die, and enrich the universe with the heavy elements necessary for rocky planets and complex chemistry. This gradual cosmic evolution would be impossible if gravity were as strong as the other fundamental forces. The universe would either collapse immediately under its own weight or remain forever as a thin, structureless gas of elementary particles. In its quiet way, gravity's subtlety might indeed be the reason we are here at all. The anthropic perspective suggests that we find ourselves in a universe where gravity is weak, not because we were specially designed for such a universe, but because universes with weak gravity are the only ones capable of producing observers like ourselves. This profound connection between gravity's strength and the possibility of complexity in the universe reveals that the most fundamental properties of matter, energy, space, and time are intimately connected to the existence of life and consciousness. Yet even as we have explored the many ways that gravity's weakness enables cosmic complexity, we have also discovered that this weakness may be far more subtle and mysterious than it first appeared. The hierarchy problem challenges us to understand why gravity should be so much weaker than other forces, leading to exotic ideas about extra dimensions, emergent space-time, and the fundamental nature of reality itself. The possibility that gravity's apparent weakness is an illusion created by our limited perspective on higher dimensional reality opens up possibilities for understanding the universe that stretch the boundaries of human imagination. The journey through gravity's weakness has revealed that our universe operates according to a magnificent hierarchy of forces and scales, where different physical laws dominate at different levels of organization. Quantum mechanics and electromagnetic forces rule the microscopic world of atoms and molecules. Nuclear forces govern the interior of atomic nuclei and the cores of stars. Gravity shapes the motion of planets, stars, and galaxies across the vast emptiness of space. This division of cosmic labor allows for incredible richness and diversity, creating a universe where quantum mechanical phenomena can coexist with classical mechanics, where microscopic chemistry can build macroscopic structures, and where local physical processes can participate in cosmic evolution. The study of gravity's weakness has also shown us how much we still do not know about the fundamental nature of reality. The hierarchy problem remains unsolved. The nature of dark matter and dark energy remains mysterious, and the quest for a theory of quantum gravity continues to challenge the brightest minds in theoretical physics. These ongoing mysteries remind us that science is not a collection of final answers, but an ongoing conversation with nature, a process of asking ever deeper questions about how the universe works and why it has the properties we observe. The experimental challenges involved in studying gravity's weakness have driven remarkable innovations in precision measurement and have revealed new ways of probing the fundamental laws of physics. From Cavendish's original torsion balance experiments to modern gravitational wave detectors that can sense vibrations smaller than 1,000th the width of a proton, the quest to understand gravity has pushed the boundaries of what humans can measure and detect. These technological achievements have applications far beyond gravitational physics, contributing to advances in navigation, communication, materials science, and countless other fields that improve human life. The theoretical insights gained from studying gravity's weakness have transformed our understanding of space, time, and matter in ways that continue to reverberate through physics and beyond. Einstein's general relativity, born partly from the puzzle of gravity's unique properties, revolutionized our conception of space-time and predicted phenomena like black holes, gravitational waves, and the expansion of the universe that have now been confirmed by observation. The ongoing quest to understand gravity's weakness drives current research into string theory, loop quantum gravity, extra dimensions, and other cutting-edge ideas that may eventually lead to similarly revolutionary insights. Perhaps most importantly, the mystery of gravity's weakness teaches us about the deep interconnectedness of all aspects of physical reality. The strength of gravity is not just an isolated property of one force among four, but a fundamental aspect of cosmic architecture that influences everything from the structure of atoms to the evolution of the universe itself. This interconnectedness suggests that ultimate understanding of any aspect of physics requires understanding how it fits into the larger cosmic picture, how it connects to other phenomena across scales from the smallest to the largest. The gentle giant of the cosmos continues to surprise us with its subtlety and complexity. Recent discoveries like gravitational waves, the direct detection of black hole mergers, and the precise measurement of cosmic expansion have opened up entirely new ways of studying gravity and testing our understanding of its properties. Future missions to test general relativity in space, more sensitive searches for extra dimensions, and the next generation of gravitational wave detectors promise to reveal even more about gravity's true nature and its role in shaping the cosmos. As we look toward the future, the mystery of gravity's weakness reminds us that science is ultimately about more than just understanding how the universe works. It is about understanding our place within that universe, about recognizing the profound connections between the fundamental laws of physics and the existence of complexity, structure, beauty, and life itself. The fact that gravity is weak enough to allow for atoms, but strong enough to build galaxies, represents a kind of cosmic fine-tuning that speaks to the remarkable nature of the universe we inhabit. The story of gravity's weakness is really the story of why we can exist at all in this vast and ancient cosmos. It is a story about balance, about the delicate interplay of forces that creates conditions where matter can organize itself into ever more complex and beautiful forms. From the quantum foam that may underlie space-time itself, to the cosmic web that spans billions of light years, From the fusion reactions in stellar cores to the chemical reactions in living cells, all of these phenomena depend ultimately on gravity being exactly as weak as it is. In contemplating gravity's weakness, we are really contemplating one of the deepest mysteries of existence itself: why the universe has the particular properties that make complexity and consciousness possible. Whether the answer lies in extra dimensions, multiverse theories, anthropic selection, or entirely new physics that we have not yet imagined, the search for understanding continues to drive human curiosity and ingenuity. The gentle giant of the cosmos keeps its secrets well, but with each new discovery, we come a little closer to understanding why the universe is the way it is, and why that should fill us with wonder and gratitude for our extraordinary cosmic home.